Welcome to one and all, present in today's webinar about battery engineering and integration into electric vehicles. I hope everyone is safe and doing good. And thanks for taking out time from your schedule and being part of this webinar. So before we start, I would like to give a brief introduction about EDS. So just a short overview about EDS. EDS was incorporated in the year 1994 with a focus of being one-stop solutions for PLM offerings with dedicated sales, implementation, and support team. Thanks to our customers and motivated employees, so we are able to retain our platinum partnership with Dassault Systems during this pandemic as well. Thanks again to our customers. In fact, we are one of the largest PLM and engineering solution house in India, supporting major OEMs, MNCs, startups, defense organizations, and academic universities. So, just to give about our customers and entire workforce. So we have close to 1,500 customers at any given point of time, where we discuss with customers on new technology challenges, new technology enhancements, and our engagement with this 1,500 customers is 24/7. Yes, of course, we have a huge customer base. We have over 5,000 customers. Next coming to, we believe in working very closely with our customers. So we have kind of 7 regional branch offices in major metropolitan cities like Chennai, Pune, Gurgaon, Hyderabad, Kolkata, Noida. And we are headquartered in Bangalore, where most of the top management, finance, operations are based out of. Yes, we have, in our growth path, we have strategic alliances with major OEMs and MNCs. We work very closely with Dassault Systems. We support their complete suite of solutions, ranging from their flagship product CATIA for product design, Simulia for simulation, Innovia for PLM, and Delmia for digital solutions. We in fact support other solutions of them as well, but prime focus is on all these solutions. To support, we have also some value-added solutions. We have tied up with certain other strategic alliance OEMs. We are tied up with Technia. We support a product named QChecker, which is used for quality checking and parameter optimization tool. We also have alliances with Human Solutions for Ramses. So this solution is based on human ergonomics. In the recent past and the need of the day, our customers are diversifying, opening up. So we also have signed up with other strategic partnership OEMs as well. We are signed up with Synopsys for power electronics related applications, EOS GmbH for 3D printing solutions for both polymer and metal, Fluster for IoT solutions, S3 for GIS solutions. Next coming to we operate through a defined teams. We have a dedicated sales, support, marketing, customer satisfaction, audit teams to address customers' immediate business challenges or immediate support requirements. Also understanding the emphasis of e-learning applications and the need of the day for skill development and industry readiness. We have also built our e-learning portal, which is a web-based training and skill development application with more than 135 plus CAD and domain-based courses. So this is specifically for the students, for academic universities. We also have some certain advanced skill building courses and exercise for experienced users. These courses are kind of it is filled with industry relevant examples and applications. We also run through a complete system integration skill sets. So this is basically we help with like startups, OEMs, suppliers of aero and auto to set up the infrastructure, both in terms of software, hardware. We also help them to get some quick staffing services. So this is a brief about EDS. Before we start about the agenda of the webinar, I just want to give a brief understanding about electric vehicles. So nowadays the first word or the most spoken word is electric vehicles, and it comes under industry segment transportation and mobility. And as of today, we speak EV as a separate solutions. Down the line, we will see it as a different industry segment. And it is at a very nascent stage. There are lots of potential in this particular segment. In the coming years, we are hearing from large OEMs shifting their entire setup to support EV production. Some typical challenges, we came across when we are working with a few of EV startups. The most relevant or most spoken challenges were on the terms of infrastructure or policy which the government has come up. They have lots of distribution problems, supply chain issues, the technology gap. They want an integration solution. They don't want a point solutions. So these were the issues most of the EVs we are working with we came across. And in fact, we have offered certain EVs some solutions in the areas of battery engineering, body structure engineering, charging infrastructure, electric powertrain, interior and exterior trims, electrical wire harness, AR and VR experiences. So that's a small briefing about EV as a segment. So let's get into today's webinar. So in today's webinar, we'll have Mr. Pratik Deshpande. He is a CAE expert, and he will be discussing about battery engineering and its integration into electric vehicles. Just to give a short brief about Pratik. Pratik is CAE analyst with a master's degree in mechanical engineering from New Jersey Institute of Technology, New Jersey. At EDST, Pratik is responsible for technical initiatives for Similia across industry segments. He works very closely with major strategic customers to understand the design requirements and provide a specific workflows with Similia products on mechanisms, FSI, vibration, co-simulation, fatigue, and failure models. So this is a short brief about Pratik. Coming to the webinar, we are open to take up question and answer after the delivery of the webinar. We are accepting all the inquiries through chat, and at the end, if there is enough of time left, we would open the audio also. So hoping this is an exciting and knowledgeable session. I pass on to Pratik. Over to you, Pratik.
Thank you, Ismail. Thank you for a very nice introduction, and good afternoon to everyone. I hope you and your family are all safe and hearty, and thank you for attending this. And like Ismail already has said, so today we will speak about how battery engineering and how battery plays an important role in the electric vehicle vertical. So we will discuss a little bit on the different workflows and the different capabilities that the workflows that has been developed by Dassault as a whole for battery systems engineering. And any questions, and if you want to know in detail about the different workflows, and if you would like to see how these workflow can help you achieve better components in much lesser time, as well as validating this virtually, you can definitely let us know at the end of the session, and we would be more than happy to answer all your questions. Now, to start with, any electric initiative, be it electric vehicle, be it electronics, the major requirement are the batteries. And as we all know that the world of batteries has been changing, quite drastically. So if we say consider a decade or two ago, batteries were mainly used to power portable equipment as well as electronic devices. But things have changed now, and today they are used in much more harsh conditions, and also they are getting bigger. Now, as a part of EV initiatives or EV verticals, batteries in the EV segments are exposed to much more harsh environment and dynamic usage as compared to earlier, or as compared to the in other equipments as well as the electronic devices. Now, batteries also, as we know, are used in wide range of temperatures. They are undergoing different temperature ranges. They are moved around a lot, and they are also moved in much harsh as well as dynamic usage as compared to previous, etc. Now, the massive usage of these batteries, along with new materials which are introduced in batteries, that is lithium-ion batteries, have brought concerns that were not so pronounced in the past. For example, we now see much more restrictions in handling and transportation. That is, while they are banned from transporting it through airplanes, or we require special packaging for truck or even rail and ship freight. Test that should be passed as per the factory norms, as per the different standards, as well as they should be handled carefully, because as we know, if damaged, they can catch fire and even explode. Now, these concerns and pose risks which should be considered earlier in the design stage itself, especially during the research and engineering of the batteries. Now, by doing so, we can take measures and safer batteries are released to the market. Now, the typical battery processes creation passes through different phases. So, research and development of suitable materials in the initial phase, then comes the assembly of cells, then assembly of combining these cells into battery modules, and then combining this module into battery packs, and finally integrating them into the final product, which is going to be our EV vehicles. And at the same time, after integrating them, they should be able to supply the appropriate energy. And at the same time, also major points are how we can reduce cost when we are designing the new battery systems. How the energy density is it providing the required energy, as well as the lifespan. We should have a better lifespan, also the better charging as well as discharge capabilities of the batteries, so that we can get good range while using these batteries. In reality, however, is that this is not easy, as we all know, because there is a lot of complexity to handle. Now, the making of right battery for the end product is always a matter of trade-off. Many criterias are there to consider, and these criterias influencing factors, as well as many scales and physics involved till the end of the product, wherein the product will come to life and then can be integrated. Now, taking EVs as an example, while customers simply expect their vehicles to be at affordable cost, which is one of the major competition point right now, they should also be able to cover long range, and also be able to charge very fast, and at the same time are safe. Now, the engineer deals with these challenges like creating reliable models for the batteries to be able to predict and test different solutions for the various scenarios. These are concerned with optimizing thermal management of the battery, and the whole vehicle being able to predict the performance and aging of the battery is also of important concern. Now, how well will it integrate with other systems, which when integrated with the full vehicle, like be it e-drive, be it your HVAC unit and car electronics, and at the same time reducing the energy consumption of the vehicle as a whole, also plays a very important role. And finally, all this is in context of very aggressive targets set globally on the battery performance and the cost that should be met to enable the widespread of EV adoption is also of a concern. And keeping all this mind, Dassault Systems has come up with different workflows and different solutions that will make that gives you access to a unified platform and make this job much more easier, and allows the user to go ahead and validate virtually. So now the question comes is, how do we innovate ourselves specifically for these concerns and take this current battery engineering method to the next level? So we have four different categories for that. So one is we move it from the electronic to the digitally connected platform. Now, when we say the electronic platform, so it's very domain specific. Tools and semi-collaboration happens, not a complete collaboration will happen. Then simulation primary in the electronic domain is an expert tool. So I am going to need an expert who is well aware of the simulation tools to carry out specific tasks for me, and to manage, migrate, and repurpose the files. Data might be lost because I'm changing it from one system to another, from one team to another. Now, all this can be negated by moving to a digitally connected platform, which is which is going to not only eliminate the silos with the digital platform, but it will also help you as an organization or as a team to establish digital connectivity. And at the same time, all the functionalities all the way from design to virtual validation can be connected and the quality of the work also is maintained, since whatever the workflow has been developed can be cascaded down to your team. So that is one of the advantages. Now, these are actually the 4 unique differentiating aspects for the 3D experience platform, which we are going to talk about. And this is what has changed for the PLM world. So we have 4 different categories here. So today we are living in a digitally connected world, and the platform for the experience needs to follow the real world. So everything is becoming data driven. So we will talk about it in the context of, say, model based in the real world. And what it really means is to be able to simulate the real world in the virtual environment. So once I simulate, my results should be very realistic or lifelike. Secondly, the results that I am achieving through my virtual validation should be as close to the real world as possible. They should, corroborate with the physical test as close as possible. And these are the 4 topics, and we'll talk about this context with respect to the 3D experience platform. So now coming to the data, going digital and going to the 3D experience. So data-driven engineering includes design and simulation across scales as well as physics. And this data enables the innovation. So this data-driven design will help you to enable for innovation, to come up with quick optimizations or come up with new different designs early in the design phase, thereby saving you a lot of money, which will eventually be spent into the testing, as well as saving a lot of time in your product development. And being model-based engineering, efficiency here is enhanced to a very high level. Engineers can be engineers without necessarily worrying about how to work with the other department, because everything is interconnected and it's a single unified platform based. And finally, it's also connected environment, which allows to leverage the ecosystem. So any changes you want to make, or you would like to cascade it down to your team, it can be saved as a format, as a file, and can be cascaded down your team because of the unified environment. And then you can leverage different expertise from different teams into your team, again thereby saving a lot of time, cost, as well as enabling a much faster product development time. Then uh, basically the 3D experience platform, the strategy used by Dassault Systems here with the different workflows is to total coverage from chemistry to the system. So the first step of Dassault Systems as a solution strategy for batteries is to provide full technology coverage. And as of today, there are proven solutions that we can definitely provide to you, all the way from 1D to 3D simulation, and scales ranging from molecular to full system as well as full vehicle level across all physical domains. And now, having said that, however, the real value is to enable tool connectivity between the technologies, and this now is achieved very nicely without any issues through the 3D experience platform. And with the current workflows that I will be showcasing to you all in the subsequent slides, we have already achieved this total connectivity. So this slide now talks a little bit about the digital solutions for the battery system. So here, with this particular workflow, is how we aim to address your challenges. So firstly, by providing full range of connected solutions for the engineering problems, be it battery management system design, be it battery module and pack engineering, or on a cell level battery cell engineering, or be it battery systems modeling, all the way up to full vehicle integration, including electric drive as well. So this slide talks a little bit about the battery materials design, wherein one of our brands, BioVia, provides the material studio, which can do more than enhanced research and numerical simulation for materials, specifically for the battery materials, such as electrode properties and intercalation, then solid electrolyte interface characterization and electrolyte characterization. Then the next area to venture with respect to the battery system modeling is the 1D simulation. So one of our brands, which is Daimola, which is our 1D system modeling tool. Now with Daimola 1D system modeling tool, user can easily build the system model or 1D model for battery system. And Daimola provides the battery library, which makes user easy to build for the own battery system. It has all the necessary functionalities to analyze the battery system, which such as battery thermal behavior, the aging behavior, the drive cycle simulation, so on and so forth. So coming to battery cell engineering, so basically, firstly, I'm going to touch base with how on a single cell level, or it can be a detailed cell or it can be a homogeneous cell, how we can carry out different physics simulations like safety, thermal, etc. And then how these can be then cascaded to battery module and pack, and finally to the full vehicle integration. So now the ability, first of all, the ability to engineer safe batteries lies first and foremost in understanding the failure mechanism on how the battery might fail. Those can be best observed at cell level when we are doing, a research with respect to the battery, where all components of battery are represented in detail and processes within the cell itself are simulated to get insight on how battery responds in different situations. So some of the methods here are considering the multiphysics. So by considering the multiphysics on a single cell level, we can reveal how the combination of electrical, thermal, mechanical loads affect the cell performance as well as the cell safety. Then by using the Resolve in 3D app, we can understand the failure mechanisms by looking inside the cell. If a short circuit is happening, what's exactly happening, what is the state of charge, or how the battery is discharging, what effects it is having, and by ensuring safety. So quality safety at cell level can be achieved to design better protection at cell, even module, as well as pack, and well as full vehicle level. So we can carry out different safety tests to see, like drop test, multi-point bending test, compression test, etc. and all. And by combining all this, we can work efficiently by using a single environment that connects your engineering data with the best-in-class solver technologies that are completely embedded and available onto a single platform. And not only that, it also makes the learning curve much easier. So coming to battery cell engineering, the full scope of battery cell engineering is very huge, and hence we have grouped them into a few categories. So we have categories like physical design definition, which involves the initial design phase. Then we have electrochemical performance. Then we have thermoelectrical losses, thermal management, strength, stiffness, durability, safety, degradation, aging, reduced order modeling, and so on and so forth. So firstly, I'm going to touch base with the thermoelectrical losses. So what are the benefits of thermoelectrical losses? So because see, whenever I'm doing any multiphysics simulation or any multiphysics study, 2 points I will be looking at as an user. What are my return of investment? Second thing, how easy and good it is for me to use these multiphysics simulations so that I can come up with a most optimized and a better product into the market. So with the thermoelectrical losses, it allows me to predict the energy losses in the battery cell, and it considers all the physics in a coupled simulation. So it can be thermal mechanical, it can be electrical mechanical, or it can be individually thermal, electrical, as well as mechanical. And with the availability of the 3D experience platform, I can connect geometry and simulation modeling on a unified platform. And it also gives me the freedom to execute these simulations onto premise or onto cloud HPC, depending upon your or the user's use. And again, I have repeated this many a times, you can manage all the relevant data at one place. So there will be no data losses. You can track the progress of your project or your program all the way from the design phase until you validate virtually and sign it off. And on top of that, we also have something called as power by approach, wherein you can connect individual or standalone tools with the 3D experience platform, wherein it will allow you to mix native and external meshes, which can be fed to analysis. And you can choose the most suitable meshes or boundary conditions or best modeling practices to come up with a better results. Then some of the studies that can be carried out during the thermoelectrical losses are, the stresses, how the stresses are being distributed, which will be a basic analysis, the displacement, then the temperature distribution, as well as the electric potential, how the electric potential is behaving. and we can enhance this simulation with full Abacus capabilities onto the 3D experience platform by leveraging different tools and roles that are available, and by combining these different roles, so be it static or explicit dynamics, along with say design of experiments, or even topology optimization, or even fatigue study, to come up with the best product with a good life, as well as shorter product development time. And this slide currently, which is displayed in GIST, shows you a workflow for the thermoelectrical losses. So in step one, we have a native or an orphan mesh or a geometry that can be imported onto a 3D experience platform. Then we pre-process the model using the pre-processing roles that are available onto the platform. Then we submit it for the analysis, and then we do with the high resolution post-processing tools that are available onto the 3D experience platform. We post-process it, make any changes required as per the constraints and objectives, and finally sign it off. Then coming next is the strength, stiffness, and safety, which is of number one priority these days, since we all already discussed how batteries are being handled in a completely different environment and much more harshly as compared to a decade or two ago. And with the strength, stiffness, and with the full Abacus capability available, we can assess the structural integrity. We can subject these batteries to external or state of charge induced mechanical loads. All these are very easily available, and the capability is very high to better understand how the state of charge induced mechanical loads behave onto given batteries. Then mechanical, thermal, and electrical characterization also can be studied out. And this slide talks a little bit about the workflow for the strength, stiffness, as well as safety. So I can import geometry or mesh of a single cell, and then I can induce a state of charge loads, which usually we call it as predefined loads. Then we can see if there are any internal short circuits, and finally we can see how the strength and stiffness is going to affect the expansion or the internal short circuits onto this battery by performing different studies like axial compression, radial compression, 3-point bending, as well as impact studies, and so on and so forth. Now, coming to the battery cell engineering, we all know that cells can be of different types. It can be cylindrical, it can be prismatic, it can be pouch. So for study purpose, for reference purpose, we are considering here a cylindrical cell. Now, by taking a single cell, either we can go with a homogenized core model to simplify our analysis in order to understand how the battery is behaving with respect to strength, stiffness, or safety, or we can even have a detailed jelly model wherein we can input all the details of the cell that is required. And once we build the model, we can we can go ahead and check whether a battery is charged or discharged, and because of charging or discharging, how the core material is expanding, specifically during the lithiation and delithiation, and the thicknesses of the anode and cathode are changing or not, and if they are changing, how much are they changing. All this can be studied. Now, the charge induces volume expansion of a jelly roll now can be implemented and simulated with Abacus. So also Abacus has the capability, so wherein the user can study the volume expansion of a jelly roll inside the battery because of the charge induction. And these are some of the demo captured here regarding strain in thickness direction as well as displacement because of state of charge. Now, coming to the next slide, which talks about coupled thermal electric displacement as well as mechanical. So internal short circuit is here we are using a mechanism failure for the separator. So all these short circuit initiation due to the deformation because of say impact or layered code representation, or to measure the internal temperature and the current in the core of the battery can easily be achieved. And co-simulation can treat easily this multi-physics behavior with minimal modeling effect. So not only we are trying to bring all this solution onto the single platform, but also the effort required to model these kind of complex battery with details is also minimal. And we can also leverage the two solvers from Abacus that is Abacus standard, which will help you to resolve the thermal electric displacement in a critical area of the battery, as well as we can also leverage the Abacus explicit solver that gives the large deformation of layers from the global cell deformation. So even we can leverage these different solvers in the form of rules which are available onto the platform, wherein we can combine this and come up, and try to study, different failure mechanisms. Also, co-simulation. uh, so passing information from global deformation at each increment also can be done. Also coupled thermal electric displacement analysis, and if required, only the critical areas in the battery also can be simulated. And on top of that, we can observe temperature and electric potential or current as a measure for short circuit onset. So all these different studies can be definitely studied. And coming to the mechanical limits in abusive scenarios, so apart from detailed modeling, there are situations where the cell core can be represented with homogenized material. Now, for example, standard physical tests like compressions, bending, and impact with rigid rod, has shown that there is a strong correlation between the reaction force drop and the temperature increase, indicating internal short circuit. Therefore, such models allows us to characterize the cell for the next level simulation, that is the module and pack, where cell model needs to be simplified, extracting the main mechanical characteristics. So be it axial compression, be it radial compression, be it 3-point bending, or be it impact, and we can characterize cell for module level simulation using this. So these are some of the examples of the axial compression test that we have already carried out. Then the radial compressions, then we have 3-point bending, as well as impact loading, to see how these cells are behaving, where the stresses are getting accumulated, and if we are having a lot of hotspots, how we can change it. Now, coming to the benefits of strength, stiffness, and safety, obviously, by incorporating or imbibing these workflow, it helps the user to assess the structural integrity and safety of a battery cell completely in a virtual environment without requirement for any of the physical tests. And we can cover both linear as well as non-linear, implicit as well as explicit behavior, including contact and damage. So all these can be included, and by including damage, we can be able to even predict the life of a given battery. And minimum modeling effort is available to resolve multi-physics phenomenon, be it electrical analysis, be it thermal and structural, and and for all this, it's a single solver. So by using the single solver, these different studies can be achieved very quickly and very effortlessly. Now, coming to the next, now we all saw what all different studies can be done onto a single cell or a single battery. Now, the next step would be to cascade those studies onto a battery pack, or the battery module engineering. So again, in module and battery pack, the structural integrity is of #1 priority to check as a product. And our simulation tools is widely used in this purpose already. Many of our customers have been using this. Now, thermal characteristics is another important behavior that the battery module or the pack designer is interested. Now, with the reduced cell modeling technique that we have, or we have previously mentioned in the cell engineering, now user can model structural analysis for safety, such as drop analysis, nail penetration analysis for the module, or even for the battery pack level. So the subsequent slide is going to talk about that. Now, the current picture shows about the thermal talks and showcases about a little bit on thermal management. This picture shows that the air cooling simulation results with different cylindrical cell packing configuration. And as shown in the slide, user can easily find out the fluid velocity and temperature under cooling by playing around with different pack configurations. So you can have an original layout which is not very tightly packed or not very loosely packed. Then you want to see how it behaves when the cells are highly tightly packed, or if they are loosely packed. So all these configurations can quickly be assessed and studied. Now, this picture talks about different scenarios for displacement, stress, strain, and damage. And this talks about, the impact analysis, wherein picture shows various structural tests described in standard and regulations imposed onto EV sector these days by SAE and ISO. So with the reduced cell model, user can easily see the individual cells behavior accurately. And on top of that, by cascading down this to the battery pack, we can show you the nail penetration and the drop analysis for cylindrical cell type as well as the pouch type batteries. So the top two images are with respect to the cylindrical cell, which have been combined to form a battery pack, whereas the bottom two slide talks about the battery pouch. So another example of the drop analysis. So abuse during now these kind of abuse scenarios can be during installation or during maintenance or even during transportation as well as assembly. And these kind of studies helps us to assess the impact resistance of the module, also helps us to assess the plastic equivalent strain or the damage variable. And this is about the penetration analysis due to impact from foreign particles. Like if I'm going at a certain speed, if a stone comes and hit my battery pack, what impact it is going to have on my battery pack, is my battery pack going to fail, etc. And these studies also help me to measure the mechanical resistance by the obstacle penetration. Now coming to the overall different types of workflows that are currently available with our battery engineering process experience. So we call battery engineering as an industry process experience, wherein you will get all the tools, the solvers with respect to the battery, the engineering of the battery, be it battery cell, be it battery module, be it battery pack, and how in the end you are going to integrate this with the full vehicle. So when it comes to battery cell, as we have seen, material characterization can be done, anode cathode microstructure studies, modifications can be done. Then ECM model can be done using our Dymola tool. Then coming to the Abacus solvers, we can do a coupled thermal electrical analysis, expansion due to SOC, short circuit, heat generation, diffusion, mechanical analysis, folding analysis, welding analysis. All this can be incorporated. And along this on a battery cell level now can be then transferred to the battery module level in the form of mechanical analysis, topology optimization, the fatigue study in order to understand the durability, air cooling analysis for both battery module as well as battery pack. Whereas when it comes to the full vehicle assembly, obviously mechanical analysis with respect to the battery once it is being integrated into the vehicle, how it's going to behave, the crash analysis for a full vehicle, penetration analysis, cooling analysis, not only with respect to the battery, but with respect to the cabin comfort and other studies can be carried out. So this is a small demo video on the different solutions that are available here through the 3D Experience platform. So I'll play them. So this is the 1D simulation wherein I can see how my battery is behaving. What would be, if I design a battery of a say 15 kilowatt, how much output it is going to give it to my vehicle, etc. Then these are the impact analysis. So this small video, and this talks about the battery module engineering, both about the penetration as well as thermal management. So we can see the battery surface temperature, how it changes when it is being heated or when the battery is started, and when it is supplying the power. These are the penetration analysis on a battery pack level. Coming back to the electric powertrain, so these can be modeled in the form of 1D to see what is the output of the machine, what are how the electric drive is behaving, and are there any options for me to go ahead and optimize it. Consider this example on a two-wheeler. So this is the initial design where the temperature is about, when you start the engine, the temperature is about 33.8 degrees Celsius. Now by using the tools and optimization techniques, I can go ahead and optimize to bring out bring down the temperature. So in this scenario, we were able to bring down the baseline temperature from 51 degrees Celsius to 45 degrees Celsius with respect to the ambient temperature, and so on and so forth. So, and this slide talks a little bit about collaboration with mechanical analysis as well as the physical test. So we have considered 3-point bending case as well as the radial compression case. And in both the cases, we can very clearly see that whatever has been validated through the virtual simulation, they closely resemble to the physical test or the actual test, thereby again proving that the solutions that we provide for battery engineering are highly accurate, and we can definitely validate and sign it off virtually without the need to go for multiple physical tests. Now coming to the next session, or the final part of today's webinar, where we talk a little bit on the full vehicle integration. So so when it comes to the full vehicle integration, like previously I said, three major categories we have categorized for the studies that can be done. One would be the vehicle dynamics, be it multi-body simulation for wheel vehicle to characterize the ride and handling, or the cabin comfort for the passenger, or how the electric drive is behaving. This all workflow comes under the vehicle dynamics. Then we have crash worthiness, so advanced explicit dynamic solver for simulation of rapid abusive events like crash, be it rollover. So what if an external obstacle is coming and trying to penetrate? So all this can be done through the crash worthiness workflow. And finally, the thermal management, which not only includes Abacus regular structural thermal analysis, but apart from it, CFD solutions also can be incorporated to simulate and assess the thermal management in the context of full vehicle. So for example, we can consider simulation of thermal soak for a full vehicle. Now the thermal soak will help us understand the impact of the structure conduction as well as the cabin greenhouse for better battery temperature and for a better better driver or a pillion experience. So all these are the different studies that can be integrated from battery level all the way up to the vehicle level to come up with a better optimized design and also bring it faster to the market. Now, how is Dassault Systems, or how will we be helping for you? How will this all fit for your next challenge? We initially I did say by going digital from electronic is the way forward, so that it will help us reduce cost, be it in the form of physical testing or be it in the form of material saving. But at the same time, we can validate all these different kinds of studies virtually. So to summarize here, the way we believe we can help you be successful when it comes to specifically the EV segment is by mastering the battery engineering challenges, and that is now completely based on the three pillars. And the three pillars are foundation, the strategy, and the core. Now the foundation here is the 3D experience platform. It's a collaborative environment to connect data, not only connect data, but it also helps you to connect people and technologies. And then comes the strategy. Now we develop our solutions to solve industry business processes, like point-wise solutions we have, which can be again combined onto our foundation, which is the 3D experience. And this in turn will help you manage more efficiently the complexity of whatever battery engineering and interconnectivity of all related systems you come across. And finally is the core. So based on full coverage of best-in-class technologies, we provide for all scales and all physics. So if you see the core, we have electrochemistry, we have materials modeling, we have electromagnetics, structural performance, behavior modeling, so on and so forth. Similarly, for the strategy, we have industry business processes. We also have methodology, wherein model-based system engineering will quickly help you to arrive at a very good results. And finally, the tools as per the requirement, the functionality, logical as well as the physical requirement. Now, coming to the end of the webinar, here we'll talk a little bit on the different workflows that are currently available for the electric drive engineering which is also a industry process. So we are not going to delve more into the technicalities of the different workflows, but as you can see, when it comes to electric drive performance, we have categorized again into different workflows, be it noise and vibration, electromagnetic performance, or be it thermal management, or cabin heat up or soak, or HVAC flow performances. When it comes to electric drive design, again, we have detailed design, we have conceptual design, we have electric drive system design, and finally, to validate virtually, we have battery engineering, which, briefly I have gone through the different battery engineering processes, as well as related processes for finite element analysis, that is the power electronics engineering. So we'll go on quickly to a few through a few workflows. So the first one being the electromagnetics. Now, achieving the highest possible power density requires a optimal electromagnetic design, which is of a must. And performance is directly related to the overall driving experience. So when it comes to this, performance is directly related to the driving experience and efficiency of the vehicle. So keeping these things in mind, the Dassault Systèmes electromagnetic solution will allow engineers to analyze electric machine performance. It also helps you to analyze the efficiency, the dynamic forces, torque, as well as thermal losses in order to drive the design of the electric machine. So this briefly explains a little bit on the operating scenario, the electromagnetic simulation with the KPIs like torque, flux induced voltage, then combining them with the structural FEM, then do a design exploration, or what we call it as design of experiment, to come up with the best design in the shortest possible time period. Then we do a design review, and finally we virtually sign it off. So similarly, we have thermal management. So the electric machine and gearbox, as we all know, are enclosed in a housing, and it becomes very complex and to model, because these need to be modeled in the form of a coupled system in a noise and vibration simulation environment. Now, simulating and predicting noise and vibration resources and paths, both structure are borne and airborne, is critical to improve the overall cabin comfort and the component durability. So by reducing the noise and vibration, it is definitely going to improve the cabin comfort, and by doing so, also the durability of these coupled systems also increases, thereby increasing the warranty as well as increasing the life of a given component. And then we have noise and vibration workflow. So this workflow is a good example for different levels of detail at different stages of the development cycle. So this, you can include all this workflow at your initial design development phase itself, or you can even include in a later stage. But by including this at different stages, we have a better chance of getting better designs in a shorter amount of time. And this slide shows the most advanced version of a noise and vibration workflow that we, as well as Dassault Systèmes as such, has come up with. And the simplest version would be just using Abacus. If you want to simplify this, I can just use the Abacus in the noise and vibration simulation environments. Even that capability is also available. Then comes the strength and stiffness, which we have already spoken about. And you can even combine this with multi-body simulation so that you can represent analytically the whole vehicle or even the battery pack. And with the help of that, we can run static or transient dynamic simulation. Then also is the durability workflow, which we briefly spoke about, wherein we can include, the fatigue analysis before we sign it off. So once our electromagnetic simulation or the regular structural as well as, dynamic simulation and multi-body simulation is done, before we sign it off, we include fatigue analysis with multi-axial strain-based fatigue methods to identify if there are any durability issues, if a component or an assembly of component is going to fail, and make modifications necessary so that we increase the durability and the life of that component, and finally sign it off. And then comes the gearbox lubrication, which is also of utmost importance, because we know that electric machine drives a gearbox, and the high rotational speed that this gearbox has make lubrication critical to system efficiency and the lifetime. Now, multi-phase simulations can be incorporated here, and it can help you minimize the size of the electric drive by optimizing the volume of the oil necessary to properly lubricate the gearbox moving parts. And because of this, the gearbox performance can be improved by minimizing the mechanical losses induced by the lubricating oil. So these different types of studies to see what volume of oil is required and how I can reduce it, so that the rotational parts do not have any mechanical losses. So examples would be like oil splashing, lubricated surfaces, oil pressure. All this can be incorporated into your workflow in order to understand better how the gearbox is behaving, how the lubrication is behaving, and based on that we can modify the simulation conditions, and finally we can modify the design and reduce the mechanical losses and come up with a much better gearbox along with the gearbox lubrication. Now, coming to the summary, so basically what are we trying to achieve through this battery cell engineering process or industry process experience? One thing is we will achieve high power density while managing cost and supply chain risk, because we are carrying out all these different studies on a single unified platform with less effort needed for modeling. And at the same time, this is going to help us save development time and cost by 1/3 or even more. Then we can optimize the performance and efficiency across multiple disciplines. So be it single cell, battery module or pack, or even full electric drive, or even vehicle integration. We can minimize risk and warranty claims by carrying out a proper durability and fatigue studies, and based on the KPIs got from these studies, we can make necessary design changes, thereby increasing the life and decreasing the recalls. And finally, we can manage occupant comfort by performing noise and vibration, NVH, as well as acoustic studies, wherein we can try to reduce the vibrations and the load bearing capacity of a given drivetrain or the motor. And on top of that, we have connected and collaborative environment, which is going to enhance cross-team work, and it is going to help you remove silos. And at the same time, if a best workflow or a best practice is being developed by an engineer, the same workflow can be cascaded down to your team, so as the quality of the work and the way the work is being done will be maintained throughout the organization. And once again, I thank you all for attending these sessions. And again, displayed onto my screen is my email. So please feel free to send any more questions. I know because of the time restrictions, we cannot answer each and every questions. So if there are any concerns, do email it to us, and we'll be more than glad to get answer all your concerns. Thank you very much. And you have a wonderful day, and be safe. Thank you.